everyone, welcome back. In this video, I'm going to focus on how temperature plays a role in solubility. In previous videos, I have discussed how intermolecular forces play a role. We also learned about how entropy plays a critical role and drives the formation of a solution through the second law of thermodynamics, that the universe just wants to go towards more chaos and disorder. And then in the video, the most recent video I had posted, I discussed how enthalpy plays a role as well in considering the enthalpy of the solvent and the enthalpy of the solute, and how the enthalpy of mixing needs to overcome both of those and be larger to make it favorable. It's not to say that an endothermic process won't work. Entropy can definitely help push things forward. But it was interesting to be able to utilize enthalpy to see how it can give us an indication if a solution will form or not, right? So let's continue our conversation. So over time, when the rate of dissolution and recrystallization become equal, then we're in dynamic equilibrium. So let's say we're preparing solutions and we make a saturated solution. What does that mean? Well, that means that the dissolved solute is in dynamic equilibrium with the undissolved solute. So if we have a saturated solution, adding more solute will not increase the concentration. And if you have a saturated solution, then for the most part, you're not going to see crystals kind of crashing out, so precipitating out. And we'll talk about that in a little bit in a second here. But let's go over what an unsaturated solution is. This solution contains less than equilibrium with the amount of solute and adding more solute will increase the concentration And then if you have a supersaturated solution, these solutions are unstable and the excess solute precipitates out. And I always like to give kind of the analogy. I come from Texas, and in Texas, we love our sweet tea. And I always would notice that in Texas, it's super sweet, and I joke that it's almost like a super saturated solution where you'd almost see sugar crystals crashing out of the bottom. And so that sugar is the excess solute that's precipitating out. So you see a solid at the bottom of your glass. Whereas an unsaturated solution should still look like water, right? There's solute dissolved in it, but it contains less than that equilibrium amount of solute. And so we could add more solute, and therefore that would change the concentration. In the saturated solution, you're kind of at that sweet part where they're at equilibrium. You're in dynamic equilibrium here with the undissolved solute. It's still like physically would look like an unsaturated solution, but in this case, if you add more solute, then you will not increase the concentration, and then you would start to witness precipitation. The solute would just start crashing out of solution. Now, these types of solutions are sensitive to temperature, and here's a graph of some solid ionic compounds dissolving in water and then based on temperature. And just like in real world applications, maybe let's say hypothetically, not hypothetically, but in real life, you love coffee, right? A lot of us do. And on a hot summer day, you may want an iced coffee, right? But maybe you don't like the taste of just black coffee. Maybe it's a little too bitter, so you want to add some sugar to it. But if you take the sugar from the sugar packets and add it to the iced coffee, it doesn't dissolve well, right? So a lot of coffee shops provide simple syrup. And what they've done is they've dissolved the sugar in warm water. And then once it's dissolved, it stays as that liquid. And you can add that liquid sugary goodness to your iced coffee and still get that sweetness, and that helps with the solubility. So they're utilizing the increase in temperature to help the sugar go into solution and stay in solution, so that when you add it to your iced coffee, it will stay in solution. Okay? And so I just want to help you interpret this graph here. So this is solubility. This is the grams of the ionic compound, the solute, in 100 grams of water. And then, like I said, temperature on the x-axis in degrees Celsius. And if, let's say, we look, for example, let me highlight one of the curves. Let me look at potassium chloride. So when you go along that line there, in potassium chloride, that is the saturated solution. So let's say, for example, I'm at 25 degrees Celsius. That's room temperature. And I'm going to go up until I intersect that line. And then I'm going to go across. And so it looks like at 25 degrees Celsius that to make a saturated solution, let me fix that real quick. That I could dissolve 32 grams approximately of the potassium chloride in 100 grams of water to make a saturated solution. Anything below that line would be unsaturated at that temperature. So for example, if I dissolved 20 grams of potassium chloride in 100 grams of water, I would be safe to say that I had an unsaturated solution. If I were to go above this line, then I have a supersaturated solution. So therefore, for example, if I try to dissolve 50 grams of potassium chloride at 25 degrees Celsius in 100 grams of water, I would have some potassium chloride in excess precipitate out, and I would see it settle to the bottom of my beaker. Okay? And so this literature data helps us to identify, it's all dependent on whatever ionic compound you're working with, but it gives us an idea of when we prepare our solutions in the laboratory if we'll make an unsaturated, a saturated, or supersaturated solution. For the most part, you generally want to have an unsaturated solution because when you're running chemical reactions, you want everything to be in general in the same phase, right? So that they can interact with one another. There are some reactions out there that might be heterogeneous in terms of the phases and states of matter that you're working with. But for the most part, when we're running chemical reactions, kind of running them in solvents and like liquids, right? So it's good to have things to dissolve. So the trend then, let's summarize that. Remember, we're always trying to think of structure-property relationships that we can gain from looking at data. So the trend here, and this is for a solid solute, I should also highlight as well, because we're about to discuss gases. So discussing solid solutes. So solubility is highly dependent on temperature. Once again, I hope this makes intuitive sense. Like you can think of my coffee analogy to help you remember that when we increase temperature, we increase solubility. Of the solid solute in an aqueous solution in water as a solvent. You will see in this graph that cerium 3 sulfate doesn't follow this, but do not worry for my course. Just assume that in most cases, when you have an ionic compound, as you increase the temperature of that solid substance going into water, that it will increase its solubility. Okay. So for example, we can add approximately 50 grams of potassium chloride in 100 grams of water at 80 degrees Celsius. So we do see that increase in solubility at higher temperatures. All right, so let's talk about gases because they behave a little bit differently. So shifting gears real quick here, let's look at gases in water. Now the trend is opposite for gases. So as we increase the temperature, we actually decrease the solubility of a gas. And the example I always like to give is going fishing. So growing up, my dad would always take me fishing, and he would wake me up at like 4 a.m. to go fishing. And I remember I enjoyed fishing with my dad. However, I did not enjoy getting up at 4 a.m., walking like a couple of miles to the lake, and fishing where it was cold and dark and there were bugs outside. Remember, I grew up in Texas. So I just never got it. I'm like, Dad, why can't we just go, when it's sunny outside and it's nice? And it turns out that the fish just do not bite as much in a warm lake. And it gets pretty hot in Texas, especially during the summer. And why is that? Why are the fish not biting as much when it's hotter outside? Let's think about this. The fish, they need oxygen, right? And if it's really, really hot and the water's really hot, then the oxygen starts to bubble out of the lake water, right? And goes into the atmosphere. And so when we talk about the solubility of the gas, we're talking about the solubility of the gas in water. I just want to make that clear. We're talking about water here. And so as you increase the temperature, the gas starts to bubble out, there's less of that gas in the water. And so, coming back to my fish, if there's less oxygen gas in the water, then the fish get sleepy. They get lethargic. And so they're less likely to bite if the water is warm. And so that's the reason why I went out fishing before the sun came up. Or sometimes we would go fishing late at night as well to tend to have better luck in catching the fish then. You can also think about if you're drinking soda or any carbonated beverage, if you were to leave it out on a hot day, it loses its carbonation real fast. That CO2 is just bubbling out there and it turns flat. It's just not as tasty anymore, right? In addition, with gases, we also need to consider pressure affecting solubility. So the trend we have here is that as we increase pressure, we increase the solubility of a gas. And the way I remember this is thinking about, once again, if you drink a soda, right? And it comes in a can and it's sealed under pressure. And there's the CO2 molecules dissolved in the solution, right? Which is mainly water. But when we open that can, we release that pressure. And so the CO2 molecules start to bubble out of solution. And so as the pressure decreases, the solubility also decreases in the water, right? But here it's under high pressure, and so there's more gas in solution. And so just to summarize, the relationship between temperature and solubility of gas is inversely related, whereas the relationship between pressure and solubility of a gas is directly related. And we can quantify the solubility of the gas using Henry's law. And that is represented as such. So the solubility of a gas is equal to Henry's gas constant for that gas times the partial pressure of that gas. The units for the solubility are in molarity, and the units for the pressure of the gas are in atmospheres. And mainly because the gas constant is shown here is a molarity per atmosphere. So that's where you can get the units there. Okay. So let's work an example problem together. We're going to calculate the mass of nitrogen in grams dissolved at room temperature in an 80-liter home aquarium, assuming that the total pressure is 1 atmosphere and the mole fraction for nitrogen gas of 0.78. So let's write down what we're given. We are given that the volume of the tank is 80 liters and that the total pressure is 1 atmosphere and the mole fraction of the nitrogen is 0.78. And we need to find the mass of nitrogen in grams. All right, so let's go ahead and get started. We know we just learned that we can find the solubility of the gas of nitrogen using Henry's law. And you may see here that we need the partial pressure of the nitrogen gas, but we're given the total pressure and we're also given the mole fraction. Now you'll have to dig back into your knowledge from first semester of general chemistry when you studied gases. And to find the partial pressure of a gas, what do you need to do? Got to use Dalton's law, and the partial pressure, we'll write it over here, of nitrogen is equal to, use the mole fraction of that gas times the total pressure. And so the mole fraction was 0.78. the total pressure was 1 atmosphere, and so the partial pressure of nitrogen is 0.78 atmospheres. Henry's gas constant we can find from the literature, shown here, 6.1 times 10 to the negative fourth molarity per atmospheres. And so let's go ahead and figure out the solubility of that gas. So 6.1 times 10 to the negative fourth molarity per atmosphere times partial pressure of that gas, 0.78 atmospheres. And we see that the atmospheres cancels out, and we get 4.758 times 10 to the negative fourth molar. 4.758 times 10 to the negative fourth molar. And I will just underline, it looks like if I had to round, it would be 2 sig figs, so I'll just keep that in mind. But we're not done yet. We're trying to figure out the grams. We know that molarity is actually moles per liter, and we're also given that the volume is in liters. So we can use molarity as a conversion factor to help us convert from liters into moles. And once we get into moles, then that means we can figure out grams using the molar mass. So let's go ahead and start our dimensional analysis setup here. So we have an 80-liter tank. We figured out the solubility, the concentration of that gas is 4.758 times 10 to the negative fourth moles per liter. And I'm converting molarity into moles per liter, so I can use it as a conversion factor, because you all know I love to cancel out units. It's very satisfying. So now I am in moles. Remember that nitrogen gas is a diatomic gas, so it's N2 and not just nitrogen. So the molar mass of nitrogen gas is 28.02 grams per mole. And therefore I got 1.06655 grams of nitrogen. Let me cancel out my moles. And remember that this will be in 2 significant figures from that 4.7 times 10 negative fourth molarity. And so I would round this to 1.1 grams of nitrogen. So we just calculated the mass of nitrogen, 1.1 grams, that was needed to dissolve at room temperature in an 80-liter aquarium, assuming that that total pressure is 1 atmosphere, and we know the mole fraction of the nitrogen gas is 0.78. We did that by using Dalton's law initially of partial pressures. We had to calculate the partial pressure of that individual gas, so that we could use that knowledge and Henry's gas constant to solve for the solubility of that gas at that pressure, and we're assuming room temperature here. And so we were able to figure out the solubility, which is a molarity. Molarity is a great conversion factor to convert from liters into moles. And we always know that if we need to find mass, then usually we have to find moles first so that we can use the molar mass to figure out the grams of that specific gas. And then round that to 2 significant figures. All right, so we discussed how temperature plays a role with solid solutes and then also with gases. And we were able to learn how to calculate the solubility of a gas using Henry's law. Thank you all for watching, and see you next time.